misunderstand and think, okay, if I were a test charge, I would travel along the field line from the positive to the negative. That's not what it is. It's that field line is showing at any point instantaneously.
Hello, Brooke. Wow. All right, Brooke. Hello. Um,
Good afternoon, Professor.
good afternoon, Amy. I actually saw you at the Columbus Circle train station yesterday and waved from far away, but I think I did anyway. Hello. Okay. So hello, Brooke. Hello, Amy. Hello. Sorry. Good afternoon, Gianna. Good afternoon, Brooke. Good afternoon, Sophia. Good afternoon, Jalen. Good afternoon, Stephen. Good afternoon, Chloe. Good afternoon, Abdel. Camera adjusting Abdel's hand. Good afternoon, Samuel. Good afternoon, Diana. Good afternoon, Jamalette. Someone else is coming. Oh, someone. Good afternoon, David. How did he just do that? Wait. Good afternoon, Brianna. Okay, we're gonna go for. Oh, I just missed someone. Sorry. Good afternoon, Sarah. Good afternoon. Good afternoon. Okay. We have a. Hold on. Let me get. Well, actually, we don't even need the board for a second. Okay. Couple of quick things. We have 2 more classes, right? Including today. Tell me if that's wrong, but 2 more classes. I want to finish. I want to get to the punchline of this whole physics story, today and Monday, but we have to be logistical first. And again, let me just say again, at this point in the year, when you're increasingly concerned about grades, I'm increasingly concerned. Let me put this a different way. I know this is the time of year where you are increasingly concerned about grades, and I'm actually increasingly confident about your grades and increasingly concerned with just getting you the ideas in your head that I want you to have for your future life and for your next science courses, and to appreciate as scientists. So again, I'm going to say a couple of quick things. Oh, wait. Oh, okay, no problem. No problem. No, that's very nice. I'm glad okay. Thank you, direct chat person. And yes, wait, what just happened? Okay, wait, hold on. We have a lot to do, but sorry, yes, we only have one more class meeting after today, I believe. I think. I mean, that's my understanding. I'm responding to a direct chat, but yes, we have today and the next day. So like, here's the deal again. This always happens at this point of the year. Let me assure you again. I mean, there's loose ends that have to be tied up. I'm going to try to. And there's logistical things, and there's academics, like your concern for your grades, which I fully know how important they are to you and in life and all of that. And it's probably more on your mind than anything about physics that I have to say. But so let me address that first. First of all, let me say again, if you're one of the people that hasn't gotten an exam back, and that is not all of you, but that is some of you, they are coming. They've been going slowly. They come sort of one at a time. And but they're coming and you're getting them, and they're good for the most part. Let me say but I apologize if you still haven't gotten one back. They're just they're happening, and it will all come out in the wash by the end. And let me say again, I don't want to dwell on it, but remember at any point, if some people have been just reaching out to me and saying, look, I totally get it, but I'm like just getting a little nervous. Can we talk about my grades? And anybody who's reached out to me, I hope I've like responded and we've exchanged information. And what I'm really trying to say again is I'm more confident about most of your grades and how they're going to turn out than most of you are. And I'm, but I understand. So if there's any more information I can give you, I will. And if you ask for it personally, I will. And I think it will all come out in the wash. But I also want to say that I just posted. Oh, hold on. Sorry, I'm looking at the chat. Oh yeah, wait. Okay, this is something in the direct chat. Oh my God, if you get your exam back, I'll just say this as a broad statement, but partly to address. If you get your exam back and your exam is, this is not a if and only if, but your exam scores in the 80s, you're definitely fine. Like an 80s on the exam means you're in A range in the course. I mean, to be like, maybe it's an A- or so, and I'm assuming that you're doing fine in lab, and I'm assuming that you've done a lot of homework and that you've been participating. But any one of you who's hearing me right now and who's been strongly participating in the class and has good grades in lab, is doing all the homework. Oh, believe me, you should not be worried. If your number was in the 80s on the exam, that's definitely you should not be worried. You really shouldn't even be worried, honestly, if it's in the mid to high 70s. I don't even want you to worry no matter what. But sure, if it turns out to be in the low 70s or something, that maybe we could just check in and make sure you do better on the final, or just look at your other grades and stuff like that. But again, I don't want to spend this whole period on this. But again, I want to say to anybody that I have any actual concern with, if I really think that that somehow you're shooting for an F or a D or even a C- or something, like, I will reach out to you, and you will not be suddenly shocked at the end. But also very quickly, let me say, as I hope you saw, there's an announcement in Google Classroom about the final exam, which we do have to have, but the final exam will be shorter than the midterm. And the point, since I know we're getting very close to it, and some of you are, you still have reasonable concerns about, I don't know how to approach this if I don't know what happened on the midterm. Let me just say again, that whichever of the two tests you end up doing better on will count significantly more in your average. So if if you know, or when you find out that you got like 80s or something in the midterm, for example, then you should be somewhat like calmed down, like you should feel okay. And then you just try your best on the final, but you shouldn't be worried that your final is going to like tank your average. So on the other end, if you're worried that you didn't get your midterm back, or you don't know what's happening with it, or you know in your heart you think you did badly, then the final, which will be shorter and which will be which will be only based on this stuff that we've been doing recently, the final will count for you a lot more. Okay, we're just the goal. Everybody who gives me something to work with in this class, if you give me something somewhere to work with, we'll work with it together for you to be judged on your best, not on your worst day and not on your middle day, but on your best. Okay. Oh, on that too, very quickly. Hopefully you're seeing a lot of the old numbers are coming back. Also, a lot of the homework things are hopefully you're seeing are like falling back into your pile. Again, to increase your confidence and give you a sense that if you've been with me and you've been in these Zooms and you've been doing stuff, you should not be panicked about how it's all going to work out. Really. But also on that, someone asked me in the other class, there is one portal which you can definitely still use. There's one game portal called Your Best or something. Of course, it's optional. But especially if you're worried at all, take any item of work that you've done. It doesn't matter whether it was already graded or not. Any item of work that you've done that you got back that you think you did really well on, or like a bunch of your class notes that you've taken that you think are really good. You take any document that you think really represents you at your best in this class and just pop that into the Your Best portal. It could be graded, it could not be graded. It doesn't matter. Just give me an example of what you think was one of your finer moments in this class. Put that in that portal. And first of all, you'll get a lot of points for it, as you see. But also that will help me, again, if there's a borderline judgment call that I have to make between two grades or something, or that's just your way of communicating to me that you are aware of when you're at your strongest. And that's the way I want to judge. The math is designed to treat you all with the same policy, but it's a policy that is meant to reward each of your best days or best selves, not just your middle self or your work. Okay. So please, again, just try, like, I'm not perfect. We're not perfect. I still owe you, some of you, stuff. And I recognize that. And that is in the system as part of it. So just saying, if you're nervous, reach out to me personally. Some of you have, and we'll talk about it. But also put something in that Your Best portal, just as a reminder to me, or as a gesture of just that. Now, hold on, there's other things. We do have to do, I'm saying this quickly, I'm sounding spazzy because for the next 2 days, what I'm really trying to urge you is I'm doing my best to catch up with grading information. You're doing your best to catch up or whatever. But you're past the hardest part academically of this course, if you don't really owe me anything. The midterm was the big hump, and it's a really long test, as you know, and that's why it's taking me so long to get through. But that was the big hump. The final is not as big a deal academically. What I want from all of you guys is the next 2 days for you to see intellectually what all this material was about. As soon as I stop yammering about these logistics, what I really want for whatever time we have left in this period and the next period, I want you to be as relaxed as you can, and I'll try to be more relaxed too, relaxed and trusting that the academics will work themselves out, and try your best just to see the material that I'm presenting to you and try to see how it tries to make sense of all the material that you've been working hard on for 2 semesters. Like on the very last day, I'll tell you how to prepare for the final. On Monday I will. As you see in Google Classroom, the final will be posted no later than Thursday night of next week. It'll be take home just as the other thing was. It'll be take home and you'll have the following Monday to turn it in. Again, hopefully it'll be shorter. Hopefully if you pay a lot of attention to the next 2 days, you'll know how to do it. Okay, but your job for the next 2 days is to worry less about the grades and worry more just about trying to understand what this material means, if for no other reason than to prepare you for PChem, if you want to be practical about it. But if you want to be, but try not to be practical for the next 2 days and just trust. Okay, I think you understand what I'm saying. So the logistics about the final, the logistics are in Google Classroom now. The actual substantive details you'll be hearing as they emerge in the next 2 days, particularly on the last day. Yeah, wait, let me get my board go. Okay, and I think that's. Oh, someone's still in the waiting room. I'm sorry. Hang on. Is someone still, or someone is still in the waiting room? Okay. Okay, I think I just got the waiting room. Okay. Thank you. Okay. Oh, and I see. So I'm answering questions in the direct chat. Oh. Wait. Sorry. All right, there's a lot. So I kept someone waiting in the waiting room. I apologize for that. And thank you, Sam. I see that now. I missed that. And yes, you can still hand in until the last class, which is next Monday. You can still hand in all back things. I mean, if I'm taking a while, you could take a while. Yes, the only thing I don't want, you can still turn in old things. And hopefully you'll let many of you are seeing at this point that if you turned in homework and you already turned in like 2 or 3 revisions of it, then by this point you get the maximum score on it. Like anybody who's worked that hard on any one homework thing, like even if it's still there's like imperfections, you're getting the maximum score on it if you've put it through the chain that number of times. And you can still do that with some old back homeworks. The only thing I don't want to take is a whole bunch of old game turns, like the special game things, sure. But the daily game turns, it's kind of silly to hand in a whole bunch. Those are supposed to be momentary reflections about the day. A lot of them you've been getting back lately. It's not worth anybody's time for you to hand back a whole bunch of old game turns. But anything else you could still turn in until next Monday night. No problem. And hello and good afternoon. Let me ask you. Okay, thank you, and thank you, direct chat. And again, if I'm sounding a little frenetic, again, this always happens at the end. I'm a little frenetic because I want to get to the end of the intellectual material with you. And because I view it as the reward of all your hard work. I want you to see what all of this physics was about before we end. Okay. And I know that I'm always sort of fighting an uphill battle to do that because I know we're at the stage where you very justifiably, you're worried about other things. So I'm just trying to do my best to ask you, if you have concerns, academic grade concerns, reach out to me personally and I will straighten out. Like if I owe you information, I'll get it to you. Or if you need reassurance, I'll give it to you, etc. But other than that, can I just see a show of hands if it's sort of clear, what's going on for the next week? That you'll great. Okay. Awesome. I wasn't even okay. Great. So from here on in, we're going to do some material, some physics. We're going to keep on going where we're going. Awesome. Awesome. Okay. And I'm going to put up the board in a second. Oh, okay. I knew there was another thing that the other reason time management is an issue with me. Before we get to the physics, I almost forgot. I've got to ask you now, and this is always awkward for me, but I need to ask you to take like 10 minutes right now to do the teacher evaluation, which, oh wait, I'm sorry, Sam, question? Or, oh, you were just having your hand up from before. Okay, okay. I think, unless, if you have a question, say, but I think Samuel, I think your hand is just up from before. Okay. I do have to ask you to do the teacher evaluation thing. And look, it's always an awkward moment for me. And sometimes I almost forget, but I put the link in Google. If you look in Google Classroom in the stream, the link from yesterday, to do this class evaluation. I do have to ask you to do it, and be honest. Of course, it's anonymous. Be honest, be thorough. I'll copy the link in the chat. I will tell you this. One of the reasons that I always find this moment a little bit awkward, I'm just going to put the link in the chat. I do have to ask you to treat, I mean, I can't make you do it, but I want to give you an opportunity to do it. And it is better to do it during class, even though, anyway. So please, there's a link in the chat. Please go to do the teacher evaluation for about 10 minutes. And what I'll ask, and yes, weirdly, fill one out for lecture and one out for recitation. They're the same thing. You could, it just means Monday and Wednesday. I mean, if you think there's a difference between Mondays and Wednesdays, make that clear. But I do need one from each class. All I can tell you is one of the reasons that I find this moment awkward is they do matter. Like, I know you all, it's possible that students feel that these don't go anywhere or that they have no influence over their professors, or for good or for bad. The truth is, I've been on the committee for years, that the college committee that actually manages these evaluations, which is also why I definitely have to do them, because it's embarrassing if I don't. And not that they know who, but anyway, but I can tell you that actually this is your moment to affect, if not your own life, the life of your colleagues coming after you. They actually are taken very seriously, very seriously. We actually do really care what you think about us, so much so that I find it off that I'm going to shut up. But please do the evaluation now. How can we say this? I'm going to ask Sam to put down his hand. How can I, when you're done, put in the direct chat if you have a question, or you can't, or the link doesn't work, or you don't know how to do it. But other than that, I'm going to just say, I'm going to ask you. Okay, great. If you've already done, so basically I'm going to ask you again. I swear they're anonymous. I swear they are anonymous. I will never know what you as an individual ever said. But if you don't mind, then just putting up your electronic hand once you've done doing it, or if you're not doing it, if you're just done and you're ready to, please put up your electronic hand. I don't know who's done what or what, but it is important that I give you the opportunity to do them. So once you're ready to move on, if you could put up your electronic hand, that would be great. Thank you. Oh, great. I was just gonna say, okay, thank you. Right, so no rush, but when you're done, please do put up your hand. Thank you, guys. Okay, again, I'm just, take your time, take it seriously, but when you're done, do please put up your hand, or if you're uncomfortable, or put it. Yes, oddly, I was just gonna say about the direct, yes, please do it for recitation and lecture. You can say the exact same things in both. Or, or you can be faster in one of them, but we do need a document for each one, which I can explain why at another time. But yes, if you don't mind, they're the same class, but they're both part of my file, so to speak. Like I take up 2 days of your life. So if you know so yes, please do it for both. And please keep your hands up if you're done. And but if you're not done, do not feel rushed. Do what you need to do. Um, I do appreciate all this, and I'll just be quiet for a second. Sure. Okay. Okay, and again, I'm just in case, so we're gonna take like 5 more minutes if you need. Again, keep your hands up if and when you're done. Hopefully if your hand's not up, it's because you're still working on it. The time, so, I mean, oh, okay, great. Okay, cool. So yeah, okay, so we are gonna wrap in a couple minutes though, either way. Okay, is that, oh, okay, great, thank you. All right, so we're almost, okay. Okay, I'm gonna say. Oh, great, thank you. Okay, so a couple more. Great, thank you. We're just about. Oh, great. Thank you. Okay, no, just keep your hands up if you're done. Sorry, I know this is, did I mention this is awkward? Okay. Okay, I'm gonna, okay, great. Thank you, direct chat person. Great. So we're gonna take our time. No problem. Oh, okay, thank you. All right, I'll slowly, okay. Okay, I think, yeah, I'm gonna hook up my board now. Again, if you're still working, that's cool. But I'm gonna slowly get ready here. Okay, the board. All right, so if you're still working, keep working. I apologize, don't mind me. But yes, but if you're not, but you can put your hands down now, if that helps. Okay. Okay, thank you. Okay. Oop. Okay. So here's the deal. Well, okay, that equation, okay. The key equation that we landed on at the end of yesterday, it's called Gauss's law. And what it says in general, okay, what Gauss's law says in general is that the closed surface integral of electrostatic field always equals the total magnitude of charge enclosed divided by a constant. What does that mean in English? What does that mean in English? What it means is, what Gauss's law is saying, it's generalizing the conclusion that we found for one dot last class. It's saying, if you draw any closed surface, if you imagine any closed surface anywhere in the world, anywhere in the lab, anywhere in outer space, if you imagine a closed surface, like a surface that closes in on itself, like the surface area of the Earth, or like a box, or like a tennis ball can, right? In other words, if you picture any container, literally any surface that touches itself so that there's a definite inside and a definite outside, that's called a closed surface. If you picture any closed surface anywhere in the universe and compute the total amount of flux, the total amount of electrostatic field coming out of that surface, what Gauss's law says is the total amount of flux coming out of any closed surface. Remember, that circle on an integral means closed. Remember back at the beginning of the semester when we had closed path integrals? A closed path was a path that closed in on itself. So, and a closed path is one where if you even keep walking forward forever, you eventually end up where you started. Same thing with a closed surface. You keep walking forever, you'll eventually end up where you started. Okay. We're saying if you take any closed surface and look at the entire amount of electrostatic field coming out of that surface, it is definitely 100% determined by just the amount, the magnitude of source charge enclosed within that closed surface. Specifically, the total amount of source charge within the volume, the three-dimensional region that is bounded by that closed surface. If you think about it, any closed surface is necessary, any closed two-dimensional region of space is necessarily the boundary to some interior three-dimensional volume region of space. Okay, and Gauss's law is saying you pick any container in the world, look at all the field strength, all the field lines coming out of that container, there will be 100, the total amount of them, the total effective field throughout the surface of that container will be 100% determined by the amount of charge you find within. And you may want to write this down. Specifically, what we're saying is it doesn't matter the size of that container. This is what we showed on Wednesday, right? It doesn't matter the size of that container. It doesn't even matter the shape of that container. It doesn't matter the shape of the charge within, just whatever amount is within is within. And it doesn't matter about any charge that might be on the outside of that container. If you want to know the total amount of field going through coming out of a container, it's 100% determined by the amount of charge within. Now, we showed that last class for 1 point. When you surround 1 point of charge with a spherical container centered at the charge, it was somewhat straightforward to see, oh, okay, the charge makes these field lines that go out. and they hit the surface everywhere perpendicular to that surface. So what we saw last Monday was, okay, yeah, what we saw was, oh, it doesn't matter how big our spherical container is. As we start making the spherical container area bigger and bigger, we might think we would catch more and more flux. But as the area gets bigger, as a function of r squared, the field strength gets weaker as a function of r squared. Like that's what we were saying 2 days ago, that if you're trying to catch field lines with a container, with a spherical container surrounding a point, like flux is field strength times area. But we found as you make the area of a sphere bigger, the surface area of a sphere is 4 pi r squared, it gets bigger at the exact same rate that the field strength gets weaker. In other words, the surface area gets bigger at the same rate that those field lines spread out and get less dense. So no matter how big our sphere was, we would catch the same amount of flux from a dot, a point located at the center of the sphere. That's what we said 2 days ago. But now what I'm saying is, you know what? We looked at that with a very simple, contrived example of a sphere centered at a dot. Gauss is coming along and saying, actually, what we saw with one sphere, if we think about it, like every dot in the world would create that situation with its own little sphere. And not only does the size of the sphere not matter, if we really think about it, we could start deforming the sphere and make parts of the sphere closer and parts of the sphere farther away. Like we could, if we think of that sphere as being made of clay or something, we could start molding it into some other shape, like a cube or a cylinder or whatever. And even though we're changing it now into an imperfect sphere, if you think about it, by changing the sphere into some other shape, all we're really doing is saying, what makes a sphere a perfect sphere is that the r, the radius from the center, the distance from the center to the edge is always the same. If you deform a sphere and make it into some other shape, what you're really saying is, I'm not going to keep r constant anymore. I'm going to make r one thing over to this corner and r something different over to that corner. That's what it means to change a shape from a sphere to some other shape. It means to now make r not constant. But what we just proved on Monday was r doesn't matter in the answer. The amount of flux doesn't depend on r. So even if you change r all around and you make it some other weird shape, you're still going to get the same result, that the flux is independent of the size or therefore the shape of the container. And that's true for every one single dot of charge that you ever imagine in the world. So put a bunch of dots of charge together, they're all going to create this effect. And in the end of the day, what we're saying is, number of field lines, what we're saying is flux through a container is fully determined by the charge enclosed within that container. Also, any charge outside the container doesn't matter, because any field line that's created by a charge outside, a field line would start coming into the container, but then it would necessarily go out the container some other wall, so it would count as zero net flux. So what we're saying at the end of the day is what I just said, that any container in the universe has a flux coming out of it that's fully determined by the charge inside. So what? What does that mean? Well, remember, and please write this down. I'm going a little, I think we said this 2 days ago and I've said it before, but remember, if you this is actually illustrating why we care about flux in the first place. Flux, just like we went from force to work to energy, because energy turned out to be something that was conserved. So it was a more useful way to look at a lot of situations where it looked like a lot of things were changing, because energy was the thing that was always staying the same in a lot of situations. We used it as a way of analyzing physics. Now, similarly, we care about flux because flux has this property of being the same for all containers as long as they're containing the same charge. But what am I really saying in English? Like, what is the point of this? And why would we end the year on such an obscure topic? Because, and here's the part that I want you to write down again if you didn't already. Remember, flux means field strength times area, right? But when we're thinking about field lines, field strength is indicated by number of lines per unit area on the page or on the computer screen or whatever, right? So remember, flux is field strength times area, but field strength is number of lines per unit area. So flux, when you look at flux, when you're drawing proper diagrams that have a proper scaling factor, where it's X number of lines per unit coulomb of source charge, then to talk about flux, to look at flux on a piece of paper or to picture flux in a field line diagram in your mind is to picture number of field lines per unit area times area, right? Right. Again, flux is field strength times area, but field strength is number of lines per unit area. So when we talk about the flux emerging from some container, some closed surface area, as we are here, what we're really just talking about is the number of lines. Like literally, and I might have said this Monday, but I'm going to say it again now. All of this obscure sounding talk about flux is a mathematical way of talking about the number of lines that go through some area. In this picture, I don't care. Like if I have a point charge plus Q here in the picture, I don't care if I surround it with a huge sphere or a whacked out like rectangular prism, as I've done in the diagram. I don't care what kind of container I surround it in. I don't care how big that container is. If 8 field lines are coming out of that charge right at the beginning of right near the charge, then no matter where I am in the universe, 8 field lines are going to come out of a container, right? What we're really saying when we say Gauss's law, as complicated as it looks and is perhaps, and as complicated as it sounds, what we're really saying with Gauss's law is field lines are conserved. What we're really saying is, look, and I'll back up and say, like, look, if you have a sprinkler of water and it's spraying water out in all directions equally, right? Like in real life, like on a yard, I mean, on a lawn, you have a sprinkler and water's coming out in all directions. If you go over to that sprinkler and you take a big tarp of plastic, like a big bubble of plastic, and you surround somehow, or a tent or something, and you put the tent around the sprinkler, and you did an experiment where you counted up all the drops of water that hit the inside surface of the tent after some period of time, right? If you counted up all the drops of water that hit the inside of some tent that was surrounding a sprinkler, if you think about it, of course it doesn't matter what shape the tent is or how big the tent is or how lopsided the tent is. The amount of water that would hit the inside of the tent would necessarily be fully determined by the number of drops that come out of the sprinkler in the first place. Like, duh, right? It almost doesn't even seem worth saying when you say it about water. If we were to literally say the total amount of water fluxing through some closed surface will be fully determined by the number of water drops that came out of the water source. Now, that is literally what I'm saying here about field. If you can follow what I'm saying about water, Gauss's law is saying that about field lines. It's saying every field line that starts at a point source will keep going forever, and no field line will start or stop spontaneously in space. So the number of field lines you get at a container is just the number that you started with in whatever charge is inside that container producing field. And I'm not tricking you. If you follow what I'm saying, that is all I'm saying. But why is it? So who cares? Because what I'm saying is, oh yes, field lines act completely as you would expect, as long as you believe that they act like water. Field lines are conserved. They're neither created nor destroyed, just like water. Easy to picture. But the revelation is, or the insight is, remember, what are field lines? Field lines are not actually thingy things. Field lines are information describing thingy things in the world. Remember again, field lines over here indicate the location, magnitude, and distribution of charge or mass over here. So field lines are just the information, the unthingy, immaterial, uncountable, or like amorphous bits of information that describes stuff that's actually occupying time and space. What we are now saying with Gauss's law is that information can be pictured as lines in a very systematic way. We can picture that information as lines, and those lines act like thingy things, like in raw information itself, describing particles in the world, in fact, obey some of the rules of particles, like they don't get information does not just disappear from the universe. Once information is in the universe, it's there. The only way it comes into being is stuff that produces it, and the only way it can go out is to go into a negative charge, basically. But once it's there, it's there. So information is conserved the same way particles are. That's part of the import of this law. The number of field lines is conserved. Okay, that's one thing I'm just trying to get across. That's the point of Gauss's law, conceptually. Now, remember again the way field lines work. I keep saying field lines are information. Remember the way field lines over here convey what's going on over there, which again is what they're doing. Like field lines are the mechanism by which any and all points in space are aware of the presence of masses and charges anywhere and everywhere else in space. Field lines are like how space retains the information of different parts of space, right? Now, remember, the way it does that is through asymmetry. I mean, the way lines do that is through asymmetry. Remember what we said yesterday? That a field line diagram is only as asymmetric as the source distribution which created it, i.e., let's look at different types of asymmetry. A point has zero-dimensional asymmetry. I mean, a point is zero-dimensional, right? It doesn't have dimension. It's a point. That means, in my mind, it has zero-dimensional asymmetry. There is not one dimension in the universe that a point treats with any specialness or preference. It doesn't treat the x-axis specially. It doesn't treat the y-axis. It doesn't treat any one dimension as special. So a point spreads field lines out along all dimensions equally. It creates lines with full three-dimensional symmetry, right? As opposed to if you had a bunch of charges arranged in a line, if you had proton, 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 all sitting like in a wire in the lab, right? Well, you can imagine each proton, each little bit of charge creates its own field lines that radiate out in all directions, right? But each one does that. Each one creates field lines that radiate out in all directions. So one over here that's creating one that's going up and to the right, that up and to the right line would cancel out with the next up and to the left one, right? The left would cancel with the right, and so on and so on. And what you'd be left with is a bunch of lines that just spoke. You see, it says cross section of spokes. If you had a line of charge in the lab, you'd have field lines radiating out in every dimension, in every direction, right? Except not along the dimension of the line, right? You would be like a big caterpillar with legs going out in all directions, but no legs parallel to the caterpillar body, right? So a one-dimensional line of charge has one-dimensional asymmetry in that its diagram is as simple as it can be. Its line pattern is as symmetric as it can be, except one axis of space is treated special. Like this is how the universe would know, so to speak, that there's a line of charge on this axis. Is the universe would see lines of field along every other axis, all spoking out of that axis. So the universe like infers, so to speak, that there's charge there. One-dimensional asymmetry creates lines of one-dimensional asymmetry. Last example on the bottom, if you had a plate of charge, a two-dimensional plane, same argument. It would create field lines that would go out perpendicular to the plane in both directions, a bunch of lines that are all parallel to themselves, so that if the plane of charge, the plate, the sheet of charge were along the XY plane, all the field lines would just be along the Z. So the universe knows, aha, there's charge there because there's no field lines. You see what I'm saying? It's always a figure ground thing. The less symmetric the field lines are, the less symmetric the charge distribution is. we know where the source is from what the lines are not doing, so to speak. But again, I'm going to say, realize the field line picture is as simple and symmetric as it can be, given the symmetry or asymmetry of the source that creates it, okay? So far what we're saying is field lines convey information by how asymmetric they are, and that information that's being conveyed or captured or represented in the field lines is conserved. Like field lines are not created nor destroyed. They sit and hold the information in as constant and rigid and reliable a way as you know, tents hold water. Okay. So it raises the question, like, if information is like static like this, can there be any changes? What if there are changes? Like, we have a line of charge like this. It creates field lines that spoke out from it statically in all directions. But what if we had a current? This is our very last, well, it's our penultimate subtopic. What if we had a current? What if we had charges? What if we had a line of charge that was flowing always in one direction? That's still a very, that's one step more fancy than what we're talking about, but it's still very symmetric, very orderly, like just a constant flow. I mean, it's a change in something, but it's a constant, reliable change. Does that create some kind of field? Is there is there a field line picture associated with that? And does it follow the rules that we're saying? Well, yes, there is, and there does. And the way we found out about what's going on with this is a man named Oersted, I mean, a physicist named Oersted in the 19th century, along with a bunch of, at the same time as a bunch of other physicists like Ampere, and Biot and Savart, during the 19th century, a bunch of physicists, primarily this guy Oersted, found out something that you may have learned about in 7th grade, which is that if you put a current near another current and isolate those currents from all other effects, it turns out the two currents empirically in the lab, we observe, we measure, we see, and we reproduce that currents going in the same direction come toward each other. Currents in opposite direction repel away from each other. So currents create field. Now, of course, it makes sense. Currents, in some ways, it makes sense. Currents are a bunch of charges. Charges create field. Okay, but apparently, once the charges, but if the charges are just sitting there in the two wires, if the charges are just sitting there, the wires don't attract to each other, because even though the protons up here are attracted to the electrons down here, the protons up here are also repelled by the protons down here. And if they're just normal wires, there's no reason to believe there's net charge in either one of them. So the attraction balances out the repulsion. If there is net charge, if there's like extra protons up here and extra protons up here, we would see something happen, but we would see them repel. Apparently, if we set the charges in motion, if we set the protons up on top in motion and we set the protons down below in motion in the same direction, they don't repel, apparently, they attract. And so this is a field. This is action at a distance, but this is not quite, and this is all, of course, based on charges and attraction and repulsion, but it's not quite the same effect as the electrostatic effect we've been talking about before. What we've come to call this as many of you may know, this action at a distance is, of course, understood to be a field. This field that seems to govern over charges that are flowing, we call the magnetic field. Now, it's still a field. It works just like any other field. Field lines, the whole thing. Okay, but this is now the field, and it's ultimately very, very much related to electricity. In fact, what we're really talking about here is the field that what we're really talking about here. We could call it a field called the magnetic field, and we do, but we could also just understand it as, oh, the fields from the electrostatic charges are now changing and changing and changing and falling into some new pattern, right? Remember that field, like each one of these charges is creating a field, but the charge is moving along, so it's carrying its field with it. So all of these radial lines are moving along all together in formation, so it creates a new pattern of field lines, which we call the magnetic field, but which is really the result of charges in motion. Now, like all fields, these field lines must be as simple as they can be, as symmetric as they can be, in order to convey the information of the source that's causing them. Well, a line sitting here would create spokes going out. I said a couple of pages ago, we don't have a line of charge sitting anymore. We have a vector, in effect, of charge flowing in a particular direction. I stands for current, right? Okay, and I know we have 8 minutes, and that's just good enough for me to land this almost final point. Remember again, field lines are the information that's just over here in space that are describing what's happening over here in space. Field lines are always as symmetric and as simple, as smooth, as patterned as they can possibly be, given whatever is unsmooth or asymmetric or complicated about the source that creates them. This source that's creating them is a flow of charge going like that, right? What's the simplest picture I can have, the simplest pattern I can imagine of a bunch of lines that indicate to space that this is happening? Well, and again, we have 7 minutes. Which is plenty of time for me to just get this point to you, and then we're almost done with the course. But we will be done with the course next Monday. And by the way, sidebar, if you can't be here next Monday, that's unfortunate. And you should really, please make sure to get the notes from someone else or watch the video. But anyway, if charges were just sitting in a line, I would say the simplest possible field line picture I could imagine to convey to the universe that there were charges in a line would be spokes coming out of that line, like would be field line spokes radiating out in all possible directions from the line of charge. That would be the simple picture of a field lines indicating the presence of a static line of charge. This is not a static line of charge. This is a flowing line of charge. It's, in other words, there's a bunch of charges in a one-dimensional arrangement, but they're all velocitizing in a particular direction. We need some kind of picture that would indicate to space that that is happening. If we just had a bunch of arrows coming out of this, that would not tell space that there was flow. Space would think, oh, it's just a bunch of charges sitting there. And not only would it have no reason to believe there was flow, but it wouldn't know which direction the flow was in. if you really think about this, and you may have to think about this, the simplest possible pattern of lines I could imagine to indicate that there's a flow in that direction would be a bunch of lines that loop. Now, this is also where I'm a terrible renderer of this, but a bunch of lines that loop around this vector. And that get, that continue on forever, that get more and more spread out as I get farther and farther away from the line. Now, I'm not drawing this well at all. That's a problem. But what I'm saying is, imagine at each point in this line, concentric circles spreading out farther and farther away from the line and going in a certain direction. So if I looked at it dead on, if I look at the line of current dead on, what I would see is lines looping around it. They're continuous closed loops. I'm just putting but they have arrowheads, not arrowheads. They're continuous closed loops, but there's arrows indicating whether they're looping that way or they're looping that way. In other words, if the line is going like this, the lines would loop in one direction. If the line of current were going the other way, then the circles would loop the other way. But what I'm saying is, what I'm trying to draw is magnetic field lines are caused by charge flow, i.e. current, they're called for some reason, the magnetic field is called the B field. I don't know why. I do know why, but it's not worth going into right now. The magnetic field is called the B field, and B field lines form closed paths. B field lines loop around because they're indicating the presence of a flow. Electric field lines radiate out from static points. Magnetic field lines loop around lines of flow. Again, and I'm trying to emphasize, because that's the simplest, because lines of flow are one step more complicated than dots of static charge. So these lines are one step more complicated than radial lines. They themselves form closed loops. That's what magnetic field lines do, right? And put another way, what a magnetic field line is, with a magnetic field line picture, is just the picture that falls into place once a bunch of if you picture a bunch of radiating lines moving along and intersecting with each other. So it's like radiating, moving along, and radiating, moving along, and radiating. If you let that happen for a while, eventually those lines would fall into a pattern, just like those waves in lab 3, when you're sending things back and forth on the long string. Eventually, these things fall into a pattern, and you just see this. Right? Same thing here. If a bunch of radiating lines are flowing along, they're crossing with each other. They'll eventually fall into a symmetric picture that totally captures the asymmetry and asymmetry of the original arrow causing it. And the picture that is a bunch of lines looping around. So we have 2 more minutes. I'm saying E field lines radiate out from a point and they're conserved. The number of lines is never created nor destroyed, and they're always caused by a point. Magnetic field lines are closed loops. Magnetic field lines are closed loops. So if you go to any container in the world and ask, what's the total amount of magnetic flux coming out of any container in the world? You will always get, no matter what container you look at in the world, if you look at the number of magnetic lines emerging out from any container in the world, you'll always get 0 because any magnetic field line that comes out will eventually come back in. Magnetic field lines, B field lines are closed. And remember again, and this is where we're ending today. And I'm going to bring the point of electric fields together with this point about magnetic fields in our very last class on Monday. When you see how they come together, that's like the point of the class, okay? But right now, what I'm just saying is the word magnetic field is what we use to describe the field that the arrangement of field lines that happens once a bunch of charges are in motion, right? And that arrangement, when we really stop and think about it, or when you just study it in the lab, you find that the simplest possible arrangement of lines that occurs once a bunch of charges are moving, the arrangement that the lines fall into place is that is itself composed of closed paths. So the total amount of electric flux through any container is always fully determined by the charge within the container, and the total amount of magnetic flux out of any container is always 0, because all magnetic field lines that go out eventually come back in. That's a lot for today. We have one more class. I look forward to seeing you there. And reach out to me if you're concerned in any way. Thank you so much for being and I'm here for a minute. Have a great day. Yes, have a great day.
Have a great day,
Have a
Professor.
great day.
Great day. Thank you. Okay. Thank you. Thank you, guys. Bye. Thank you. Awesome. Thank you. And okay, we'll stop the recording.